All right, hello everyone. My name is Sharon White. Welcome to today's webinar, our Engineering Roundtable, Verification of SoC Designs. I'll be the moderator for today's chat. Today's webinar is an open format. We'll hear from our BLT engineers on verification and answer your questions. Our engineers will speak for about 20 minutes and then get to your questions. Please use the chat panel to ask questions and I'll ask the engineers for you out loud. A few notes, today's webinar is being recorded and we'll send the recording out when it's ready. That should be in a week or less. We also recommend you put your Zoom into gallery view today for the best viewing experience. The icon for that is in the upper right-hand corner of your screen. And you can change between speaker and gallery view. So definitely check out gallery view. Before we get started, please let me introduce to you the BLT and our team. BLT has been in the design services business for over 30 years. We were started by one of the original Xilinx FAEs. Our headquarters are in Maryland, and we also have an office in Melbourne, Florida. We design chips, boards, software, and complete systems for commercial, military, and intelligence clients. Our designs are in space, undersea, and everywhere in between. And we've been AMD Xilinx training for 25 years. We're an AMD Xilinx premier design partner and authorized training provider. Our training is by engineers, for engineers. We bring our decades of real world experience to the classroom. So today's speakers are Cole and Ellie. Cole is a project engineer at BLT with a focus on RTL design and verification with FPGAs. In his career, Cole has focused on verification and design on software-defined radio, defense systems, and industrial network systems for commercial and defense clients. And Ellie is an engineering manager at BLT, primarily focused on ACAP, which is now Adaptive SoC, RF SoC, and MP SoC designs for both commercial and defense applications. Ellie has spent many years managing Xilinx-based FPGA projects. Before coming into this role, he spent countless hours designing, integrating, and debugging radar systems, underwater sensors, and cryptographic ASICs. Welcome, guys. Before we get started, I'd like to tell you about a few training opportunities we have coming up. If you're interested in learning more about verification, we have a class coming up in July, which is Designing with Verification with System Verilog from July 18th through 20th. It's a 3-day class. Cole will be teaching that class. We also have our Vivado Bootcamp for the FPGA user, FPGA Essentials, Architecture, Memory, and I/O, which is June 27th through 29th. That's also a 3-day class, and all of our classes are $299 a day. We also have a no-cost 4-hour workshop on the Vitis Model Composer coming up on June 21st. And we have a webinar in July on the brand new Vitis release that the email went out this morning on Vitis, the new IDE. So I'll put those links into the chat panel for you. All right, guys, I'm going to pass it over to you to talk about what we're going to go over today.
All right, hi, everyone. We have a few topics that we'd like to cover, just general best practices around verification when it comes to Xilinx SoCs in particular. So we'll look at the SoC verification best practices, how to utilize verification IPs and the different VIPs that are available within the Vivado ecosystem. We'll also take a look at how to leverage cross-triggering, which is a technique for debugging your live hardware with running software code and using it, to have the hardware halt the software or have the software breakpoint halt the hardware. And that will obviously work with inside of a logic analyzer. So the format of today's webinar is really just an open discussion. Cole and I have spent a lot of time working with these various technologies, and there's a few things that we want to share. But obviously, if there's any questions or things like that that you'd also like to hear from experts, by all means, please place them in the chat, and either Sharon will, graciously interrupt us with those questions, or if we see it, we'll be able to get to them. So this session should be as interactive as possible. Make active use of the chat to do that. So with that, I'm going to stop sharing the screen, and Cole and I are just going to have a conversation.
Yeah, so I guess, Ellie, our first topic was the SoC verification best practices. that was our goal. So yeah, one of the things that I've always emphasized to teams, and it gets varying levels of resistance because we're all engineers and we hate documentation, but writing a verification plan is always a really big deal for me, especially doing things from like a module level, and then also ensuring that modules and different aspects of your design can communicate properly. So verification plans, an ideal verification plan is going to be able to lay out the entire design and its goals, and then also show you exactly how you're going to test it. So it's a really good reference for anybody, whether you're doing the verification or trying to kind of second check or double check everything. It's just a really easy way to go through and kind of validate that you're covering all of your cases. And it also helps from the perspective of getting kind of like really easy third party help as well, as far as pointing out any holes and that sort of thing. So
And you bring up a lot of good points there, Cole, especially for when we're working on designs here. Obviously, we're always documenting and designing before we put any code down in the IDE. And so the same, as part of that process, you also want to document, how am I going to actually test that this is going to work? And sometimes people will find that when they work on that upfront, they'll actually maybe discover assumptions that they might have missed. You know, a lot of times I like to look at it from the perspective of, if I'm the guy on the bench trying to test this later, what are the things that I'm going to want to have up front or have prepared for ahead of time, so that I don't have to, you know, incorporate that later and I can't budget my time effectively.
yeah, exactly. And one of the other things that goes really well, kind of partnered with verification plans, is building like kind of the structures that come from UVM. Maybe not specifically UVM, because the stand-up time on that can be a little extensive sometimes, but even just making like short tasks that are going to just create a forever loop, and then just forking those tasks, and then effectively just constantly monitoring the output of some module or something, just to validate the formatting of your data and that sort of thing. So I use that all the time. And once you do it a couple of times, you can toss it together, and you can toss small ones together in a couple of minutes, and larger ones in maybe an hour. But then you never have to hand check that section again, as long as it was implemented correctly. So
It's also useful from a reuse perspective. So, you know, I have a task that makes sure all my clocks are running and make sure that I'm at a reset, and I can reuse that on every project that I work on again and again. And then as my clock frequencies change, maybe there's different things that I check with respect to the clocks to make sure that they're all running at the frequency I expect them to. You know, those types of things could easily be reused. Other things from, and this also kind of segues into the next topic, which is the verification IPs. You know, especially in the SoCs, you know, what are some very effective ways to, you know, ensure that we're properly simulating all of our interfaces, and a lot of times that's utilized through bus functional models, BFMs. So old school would typically call them BFMs. Now it's more common to see them as VIPs, or verification IPs. So there's quite a vast library of VIPs that either come with the tool or could be purchased separately. But the main premise is that they remove the need to have to test the interfaces. So for example, if I'm using a JESD core from the Vivado library, Xilinx has already done the work to test that JESD core works correctly. So I don't need to test the high-speed serial I/O, which could take tons of time from a simulation perspective because of how many transactions need to be recorded. But what I can do is I can put the complement of that IP in my test bench. And that could be a very quick way to have, you know, the transmit and the test bench, the receive in my design, and have a JESD interface that I could use in my simulation environment.
yeah, and then also getting access to kind of in a similar vein, like traffic generators and that sort of thing. I know that Vivado has some modules for that are even synthesizable, so it can like help expedite a lot of your a lot of your processes, because especially sometimes when you're working like in just general test benches and you need to generate stimulus, if you're working in one of the older languages like VHDL, you can spend hours writing out lines and lines of code with your delay statements in between to assert your signals, and then also double checking to make sure that you're not out of the period of your clock, or I'm sorry, the phase of your clock. So then your traffic generators can really help with that in a lot of ways.
Yeah, certainly, we find in a lot of data flow type designs, AXI stream is very common. And so it can be used, typically like your JES IP will have an AXI stream output. PCIe for the DMA controller aspect will have an AXI stream. The traffic generator can create AXI stream packets with TLAST and things like that, that can be very useful for providing stimulus to your test bench and also stimulus on the bench as well.
Yeah, and correct me if I'm wrong, but if I remember correctly, that traffic generator can also you can like format packets and like the data that comes in like each specific word as well. So then you can kind of like preload it with your data, and it kind of streamlines that process as opposed to having to do it in like an actual test bench.
Yeah, exactly. So yeah, you can configure the traffic generator in custom mode and give it the data that's going to be put out over that interface, and it models. It's a bus functional model. It models what the interface is supposed to look like. So AXI stream is more of a simple case, but things like AXI memory mapped and having create all the logic to do memory mapped and burst transactions and things like that. We don't want to have to test those things that are known and good. We could just use the IP and make sure that it's working correctly. And then even a further point, the Vivado library has protocol checkers. So if you're working on a block that has an AXI interface and you want to make sure that it's following the AXI spec correctly, especially if this module is going to interface with an MP-SoC or the Versal SIPs, you can put a protocol checker on the other side to make sure that everything you're doing is following the rules of AXI like it should.
Yeah, and kind of going back to like our best practices, one thing that I've seen in some verification environments is that like especially when engineers are verifying their own code, it's really easy to kind of get tunnel vision and verify off of the assumptions that you made while you were coding the RTL. So then you kind of get into this like confirmation bias loop where you can only verify the things that you're predicting, and then you kind of miss out on situations that you're not considering. So then like those traffic generators and those verification IPs can kind of prevent you from having to design both sides of the interface, such that like you're generating or you're creating the master for the verification side, and then you have a slave device and you need to validate that the interfaces are working correctly. You can kind of avoid that issue by using those traffic generators. So that's another really good use for them as well.
Yeah, I did want to share with everyone here a piece of IP that we use often here, which is the AXI verification IP. So I'm just going to put that in the chat here. And the AXI verification IP allows you to direct AXI transactions to your peripherals. So if you have an MP-SoC, a 7 series SoC, or a Versal device, you could use this to emulate your interfaces. You could also use it to emulate memory interfaces to act as a scoreboard or a checker. There's a very simple API that you can leverage in a System Verilog test bench for this. And so, and just one second here, there's a question from experienced designers typically need to use an evaluation board to verify SoC designs, software and firmware. Does AMD have capability to emulate the processor in simulation? So great question. That's basically what I'm answering right here. The verification IP, that's one way to do that, and we use that IP often. Another trick that we use is we create register maps or register spaces for every clock domain in our design. And so that way we don't have to maintain a single large register space that might have multiple clock domains all coming into the same block. And then we can manage the clock domains through an AXI interconnect or an AXI smart connect as a way to make sure that the clock domain crossings were handled correctly, and we could test those interfaces. So there's that link that I just sent for the verification IP. And then there's another link here for the SIPs IP. And so what this lets you do is there's essentially a VIP, an AXI VIP inside of the SIPs, and you can use this to command AXI transactions out of the SIPs block. There's a similar infrastructure for the MP SoC as well. So I hope that answered the question.
Yeah, and I was going to say one thing that I also think that it's important to note is really at its core, the processor side, like the software side of these SoC devices, are really just going to be communicating through the AXI transactions. So while you're not directly simulating your software, you can kind of simulate your software and see like the data that's being transferred by the reads and writes, and then kind of use that to model the data that's going to come in and out of your AXI verification IP and that sort of thing. So that's one way that you can like pretty easily lift it and tie it into your system. So
yeah, another good best practice for people who work on software. Typically, what I recommend is whoever's designing the software do a log printout of all the reads and writes that you're doing while you're testing your bare metal code, for example. And then you can take that and put it into your test bench, because ideally you want your test bench to match the commands exactly. So there's another question here. Would the designer need to translate the processor instructions into commands to drive the VIP? So the VIP is not synthesizable. It's only possible to use in simulation. And there's a simple API. The way you get started with the VIP is if you right click on it, you can do an open IP example design, and that'll give you a test bench that shows you the commands to read and write through AXI. There's a lot of different configurations for it. So if I have someone writing software, they can write to a particular address in the programmable logic, and then you can just translate that over to the API call in the VIP. There, you could use an Excel spreadsheet or however you format those outputs that would let you do that. Cole, you want to take this next question here?
So yeah, the question is, hi, are these IPs embedded on the basic SoCs installed on Vivado? So yeah, correct me if I'm wrong, Ellie, but I believe that they're just part of the Vivado library, so they can just be integrated. And like you said, with that example design, they're just going to be there to model your SoC device. So it's actually not. It's almost going to be agnostic of the SoC device you're using. It's just going to be, or because of the fact that it's in your verification environment itself. So then it's kind of agnostic of your hardware, and you can just
yeah, the second link that I sent shows an example with the Versal device. There is another place that has a similar example for the MP SoC. Basically, if you have the SIPs in a block diagram, you can you just have to kind of tell the API where, hierarchically, where is the SIPs so that it can connect to it. And then the only requirement before you're able to send transactions is that you have to give it a power on reset and tell it the clock source. And once you tell it that you set power on reset, that it's no longer in reset, and it has a clock source, you can then start to send transactions through a simple API.
Yeah, so there's definitely a lot of ways to verify your SoC design as far as like simulation goes, but then going to kind of like the cross triggering topic. So then that's like moving on to like the actual bench, and then also, so then cross triggering is the concept where you can have your breakpoint in your Vitis software trigger an ILA to capture data, or vice versa. So you could kind of, it gives you that visibility into where each one of your designs are at when things are happening. So then you can kind of figure out the timing if things are incorrect. Given this is going to be worst case scenario, I really don't think that that anybody wants to be debugging software and hardware interacting with each other on the bench itself. But yeah, so cross triggering is something that's really useful in those desperate times. But so it's just it's something just to kind of keep in your back pocket for sure.
Yeah, I'm going to put a link in the chat on cross triggering, right? Effectively, what this is the ability to have software send out to the trigger port on an ILA, which you have to enable that trigger port. And then vice versa, the ILA can trigger the software. And ideally, so if you're very methodical about how you approach verification, before you ever even touch hardware on the bench, your design should be fully simulated to make sure that it's working correctly. And so then one of those places where you typically find, I put it on the bench and it's just not working. There's a few reasons for why that could happen. It could be an asynchronous signal issue. It could be a board feature. I call it feature, something that was on the board that wasn't planned for. Like I assumed that the reset coming off the board was active high, but really it's active low. So that kind of thing, I'm sure that's happened to some of you here before. We might have issues with clock domain crossings because obviously when we're doing a behavioral simulation, if we're not doing a timing based simulation, we wouldn't be able to catch that. And then also communication. So especially when software is in the loop, oftentimes it's not necessarily the same person. So sometimes the software person and the hardware person, they don't communicate well, and an assumption is missed on how the register was implemented, for example.
Yeah, it sounds like you're just kind of reinforcing my thoughts on verification plans with the communication between teams. But yeah, that's definitely one of the biggest things is I mean, when you're going to the bench, just really ensuring that you are communicating with the software. And even if you've got to go make them sit down with you and go over some things, then I mean, it's better than trying to debug something on the bench for however long. So I mean, one thing that I've heard, and I say myself, is like an hour of verification is worth a day on the bench. So if you can try to avoid the bench at all, then you're saving yourself tons of time. So
Yeah. And we were talking, Cole and I, before this, what are some of the things we want to talk about? And you brought up an interesting point with this deterministic random bit generator that you're currently working on. That sometimes, and this kind of segues into the logic analyzer topic, that sometimes you don't always want to trigger immediately. What was that situation we were talking about?
Oh yeah, so one of the cases that I was actually having on a design was that there was kind of some miscommunication between some documentation on an IP and then what was actually being realized. So I had to try my best to utilize the ILA to try to figure things out, and one of those things was the state-based triggering. So I actually had a specific case where, as defined by NIST with deterministic random bit generators, you have to have some sort of health test that effectively verifies that the system is working. And if it doesn't work, then it bricks itself, just to help protect the system and the peripherals that it's potentially seeding. So I had a very specific case where it would fail maybe, I don't know, 5% of the time or something, the health test would. And to kind of help ease myself as far as having the ILA trigger properly, using that state-based triggering, I was able to figure out a very specific case that would only be true when my system was failing, and I was able to cause that to be my first state, so then I wouldn't capture the things that happen consistently between every single run, regardless of failing or passing. And get a full scope of my data, because really the alternative was to run it once and then, or I'm sorry, set up the ILA to start triggering and then run it once and then just repeat that over and over until it finally works. So I was able to avoid that and then also capture the data using by adjusting the trigger location in the window as well. I was able to capture all of my data, even though my trigger was kind of one of the last things that happened. So.
Yeah, and I think it's actually pretty easy to enable that, right? It's just checking a single checkbox in the ILA IP configuration, right?
Yeah, the state-based triggering is really just one checkbox, but then you just have to be very specific about like transitioning between your triggers. So it's kind of like a unique language where it's like a cross between Vivado and, or I'm sorry, not Vivado, Verilog and maybe like C or something. So it is kind of its own language, but once you get the basics down, and really the language itself is very basic, then you can really do a lot with the state-based ILAs and save yourself a ton of time. So
Yeah, that trigger state machine logic, I think that's over in the language templates on the left-hand side and the flow navigator on Vivado, there's some trigger state machine logic in there for all that syntax if someone was looking for that.
Yeah.
Yeah. Other things that that are worthwhile to talk about from a verification perspective is how to manage and come up with the sequences and the tasks that you're going to have in your environment. How do you quantify that you've really tested or covered everything that you need to make sure that the design's working as it should?
Yeah, so one of the things that I've kind of learned is it's like kind of a cost analysis of of the two paths when you're creating sequences. You can either create large ones that are very specific to your use case, and oftentimes I will only do this when I have like kind of a one-off sequence, or I'm sorry, assertion that I want to write, and it'll just kind of be like a very specific case of what's going on. But then the other situation, and this is for reusability, if this is something that you're going to be repeatedly testing or maybe kind of propagating as you go up in the hierarchy, is creating smaller sequences that are looking for maybe a single transition of signals or a single relation between the signals, such as like your valid going high and then your ready asserting within so many clocks of that. And then you can kind of call those sequences in larger assertions and kind of just create building blocks with that. So it's really useful as far as reusability goes and clarity for everything. So.
Could you explain? I don't know if everyone here maybe understands what assertions are. Could you explain how they work?
Yeah, so assertions, they're just going to be kind of a compilation of condition or signals and signal transitions or maybe values that you're expecting in your design. So you can effectively picture it as like your first sequence in your assertion is going to be the trigger that's then going to start evaluating. So like you may look for a valid signal in your first sequence, and then after that it's kind of open to whatever you have following, and then you can just verify a very specific set of things. So you can validate in your verification test bench that maybe a specific control bit is being set to start to kick off a process or something like that, just ensuring that your timing and everything is in line with like maybe a signal that kicks off your design or something like that. So yeah.
Yeah, those types of things could sometimes be very difficult to find, like lining up the timing of when do I read data coming out of a FIFO, for example, or
Exactly.
maybe adopting code from someone else and having to line up their timing correctly instead of just assuming what the timing is.
Yeah, so in my experience, I've kind of noticed that assertions are going to be most useful for situations where the timing between signals is really important. And then if you have any requirements for like data being formatted in a specific way, or even ensuring that data that's coming out of like maybe a beamforming pipeline or something like that, you can use kind of checkers that are actually going to accept the stimulus that that your beamformers is using to create the output, and then you're effectively going to model that in kind of like higher level system Verilog, or you can even do it in C or higher languages by communicating between the two languages, and then you're effectively just calculating what you're expecting and then comparing that to what the test bench actually outputs, and then that's how you can kind of automate your like more math intensive designs as well. So.
While you're talking, a little bit unrelated, but another best practice I was thinking of is, especially with a lot of Vivado designs using IP integrator. A lot of people often ask me, how do you simulate the block diagram, right? And so it is possible to attach to the block diagram hierarchically, and you could actually put your bus functional models, you can stub them in for your interfaces. So for example, if I have an ADC, if I'm using an RF SoC, and I don't want to simulate the data converter, I can put a traffic generator, an axis stream traffic generator in the test bench that hooks in to where the data converter connects to my data flow. And then that way my simulation will go a lot faster. Because the reality is I just want to, at a system level, test everything internally and make that go as fast as possible so that I could do more iteration cycles on it, right?
Yeah, so then aside from the IP integrator as well, there's like other situations where and this is if you're working with an entirely system Verilog environment, then this is capable in Vivado, but then other third-party simulators will accept it pretty much everywhere. But you can also kind of dig down into the hierarchy of your top level test bench and assign signals. So then you can actually tie those signals to maybe a net that's just hanging in your test bench. So maybe if it's down like 3 hierarchical blocks, you can actually connect those up to like a BFM or something like that, and then provide stimulus that way as well. So it's a way to like modularize it at the test bench level too.
Yeah, I think sometimes when you're designing your test bench, yeah, people will try and shoot for, let me put the whole system in there.
Yeah, exactly.
And then that could lead to simulations taking, overnight to run, for example, where if instead your simulations are just very minimal and efficient, with not a lot of higher level things needing to be, addressed by the processor, your sim time could speed up drastically.
Yeah, exactly. So I always emphasize like trying to keep your simulations as lightweight as possible.
Mhm.
I kind of also operate on the confidence that my previous test benches have um, validated the submodules, so then I can kind of pick and choose what verification aspects I do want to keep in if I have like a monitor or something like that. So then it kind of also helps reduce the work for the calculations per event as well. So you can help keep your test bench lightweight by just removing maybe old artifacts or artifacts of older test benches as
Yeah.
well. So.
Yeah, I mean, we have, for example, we take the AXI verification IP and we use that to simulate our register spaces, and it literally takes 5 seconds or less of sim time to test like 100 registers, just because the test bench is so minimal. Everything's in the same clock domain. It's a very quick way to say, hey, my register bank is doing what it's supposed to do.
Yeah, and then like to tie back to what I was saying, I've seen some cases where people will kind of keep that, or in a situation where they had a register space in a level of hierarchy, they would keep that verification IP uh, in their test benches in the higher levels of the hierarchy, when that's truly not necessary because you've already validated that it's working with that lower level test bench. So then um, you can kind of call that verification IP and speed up your designs or your test benches.
So I think we've pretty much covered, a lot of the best practices that we want to share, the verification IPs that are available, such as the SIPs VIP, the AXI VIP, the test pattern generator or the traffic generator, protocol IPs, using the complement of your high-speed serial IO, such as like the JESD, PCIe, gigabit, Ethernet, things like that. We also kind of went over how cross-triggering works and situations where you might want to use cross-triggering, and the advanced state trigger state machine and the logic analyzer. So we kind of covered quite a lot of ground in only about a half hour or so. Sharon, would you like to come back here and moderate any questions we have?
Sure. And if you guys have questions, do please put them in the chat panel and I will read them out loud for for Ellie and Cole. I do have a couple of questions that came in. The first one is, does Vivado have support for UVM?
Yeah, so Vivado is going to support some of the more it's not going to support UVM as its methodology with its library, but given that UVM is a methodology itself, it supports a lot of the aspects that are used to implement UVM. So that's kind of what I was talking about, going back to those tasks that can kind of model a monitor. So then you can just kind of drop those into your designs as necessary to kind of circumvent the limitations of UVM, because it is such a heavy lift for the software as well. So.
Yeah, Vivado does support some aspects of UVM, but not the entire suite of it. And if anyone was looking for that, the simulation user guide kind of goes into, for UVM and System Verilog, what the supported features are.
All right, the next question is, in practice, what types of designs have you seen cross-trigger be used in?
So for me, I've seen some cases for cross-triggering where it's been dealing specifically with packetized data, especially when you're dealing with like maybe Ethernet or something where you have a very specific pattern that you're expecting out of your Mac, and you can kind of use that to either trigger an IL or have your ILA monitor the data coming off of your Mac to look for a specific header word for your Ethernet packet, and then maybe trigger the software so you can see where the software is at, almost as a reaction of the packet coming in, or the opposite, where once the software receives the packet and starts processing, you need to kind of understand what the hardware is doing in that time. So then you can use that breakpoint to trigger your ILA and get some vision into everything. So yeah, packetized data is a really big use case for it.
All right, next, are there any IPs available for stimulating designs while on the bench?
Yeah, that's a great question. We mentioned the AXI traffic generator. Other features of the traffic generator, so you can configure it as an AXI light, AXI memory map, AXI streaming. There's also some pre-canned infrastructures for video data, USB data, things like that. So common protocols that you might run into. We will typically use it for simulating, making sure that our DDR interfaces are working correctly. So we can have data be sent, read and written to the DDR external memories to make sure that calibration passes, that our boards are working. And then we can also use that in simulations as well. And then you also have the protocol checkers. Those don't provide stimulus, but they can look at the result and make sure that everything looks okay. And then finally, using complementary IPs. So if I have 1 gig Ethernet Mac in a transmit mode, I can have another one in a receive mode, and I could use them to work together in those situations.
All right, we have another question, and I apologize because there's a lot of acronyms, so I might screw up how you pronounce these. Does AMD integrate support PS architecture for QEMU environments?
So it's a great question. The QEMU environment is an emulation tool that is actually third party, and many vendors provide support to within QEMU. And one of the ways that they do that is that the CPUs under the hood are supported. So Xilinx has, and QEMU organization has support for all of the processors used in their SoCs. So that includes the A9 processor in the Zinc 7000 series, the A53s and the R5s in the MP SoC, and then the A72s in the Versal architecture. Now, when it comes to actually using QEMU, there is a few limitations. You can emulate everything from the processing system side within your software, but you cannot emulate interfacing with hardware. So if you have a register space that's outside the AXI interface going into your PL, you wouldn't be able to emulate that in QEMU. Now, new for Versal is that there is actually a system simulation capability where you can do a QEMU-based PS simulation with the Vitis analyzer for your AI engines and your graph code and the logic in the PL. So you could have a three-way simulation to emulate your entire system. It is very handy. It does consume a ton of resources to get running though.
Yeah, not only is it going to consume a ton of resources, but then there's also the time aspect of it as well. So if you get to kind of the level where you're going to be integrating all three of those environments, you should guarantee that you have a very high level of confidence as far as the operation of your design goes. So that way you can only, or so that way you potentially only need to run your top level test bench once just to validate that things are working. But and kind of not use it as a way of testing that your design is functioning properly, but more so just testing that everything is working together properly. So not looking to validate any specific module, but the system as a whole. And then you can kind of avoid running it so many times and keep that runtime low. So.
All right, are there any other questions? All right, I'll wait just another second or two. If there's no other questions, then a quick plug, if you're interested in seeing some of our on-demand videos from previous, we do have a cross-triggering demo, which you can check out on our website. And we do have our course calendar, which does have our upcoming no-cost workshop and other webinars, including a walkthrough of the new Vitus 2023.1 and our class on verification, which is coming up in July, which Cole will be teaching. So last call for questions. All right, well, we appreciate you all for joining us. Thank you, Ellie and Cole, for sharing your information with us today.
My
Yeah,
pleasure.
thank you.
Have a good one, everyone.